Good morning, Astronomy 1010. It's Monday morning, or Monday afternoon, technically, and today begins lecture 2, our second week of lecture. Today we'll be having a lecture on coordinates and the moon, and maybe even some timekeeping stuff. And then we'll be doing our lab number 2, which is on the celestial sphere. I'll be training you on the use of equatorial coordinates today so that you can hunt down and discover the brightest and most famous stars in the sky. And this is a really fun lab when you do it in person. Unfortunately, we'll have to kind of do it together using my iPhone as a camera. It'll be less than ideal, but we'll make it through, and you'll still learn a few things about some famous stars in equatorial coordinates. For those of you who print out their labs in advance, all we'll really have time for today, if experience is any indicator, are the first 2 pages of today's lab, okay? So if I share screen very quickly with you to show you what's up, if you have a printer, you guys should open up Lab 2 and just print pages 1 and 2. So this page and this page, and that should be all we need. If not, you are going to have to copy these tables down onto a book so that I can see the questions as well as the answers. And before we go, I kind of have to have a talk with the class in general, because last night I stayed up late grading your first homework in your first lab. And the vast majority of you did exactly what I wanted you to do. You watched my videos. You watched me do the lab and do the homework. We did it together, and you wrote down exactly what I wrote down, and you turned that in. That's what I want. There are some of you, a few of you, who I suspect maybe aren't watching the videos or didn't get the message, but some people tried to do their homework like on their own, in their own way, with predictably bad results. And I don't want you doing that. I don't think you guys are experienced enough yet to kind of handle some of these questions on your own. I want to be your tour guide through them. I want to do them with you. What's especially frustrating is some people were typing up their homeworks and they did not hear my instructions, which was, if you are going to type your homework, you need to use an equation editor for all the math that you do to make it look professional and readable. And if you don't know what an equation editor is, you probably shouldn't be typing up your homework. I did try to explain that, so I don't want to waste too much class time on it. But if you have a Microsoft Word document, which is probably what most of you guys are using, you have to make your mathematics look very good. You have to go to Insert, you have to do Equation, and you have to use all the proper symbols that we use in class. If there is a fraction bar, like if we were doing the angular size formula from last week's homework, or maybe from this week's homework, you actually have to use fraction bars, right? And you have to use units, 360, and then you've got to use the little degree symbol, which I think is up here. You've got to figure out how to do this. I don't know if I have time to explain all that to you. I'm trying, but and if you can't, 360 degrees divided by 2 pi. This is how your stuff has to look, and you have to have units and all that stuff. And if you can't do that, well, then you don't have the right to type up your homework. Now, it was so frustrating, and it wasted so much of my time last night that I am this close to making a global announcement for the class, which is no more typed homework. You have to write it up and take a picture. Now, I don't want to do that, so I'm going to give you 1 more week to straighten it out. But if I get another round of crappy, typed homeworks like that, I'm probably going to ban them altogether just for my own sanity. And I probably won't have time to put the extensive comments that I did, because there's so many of you in this class. I ended up writing the same comment like 30 times, and it was a comment I already explained in the class during the videos. So I just can't do that anymore. It's too crazy. So this probably doesn't apply to many of the people I'm talking to, because you probably just did it the right way, but I have to try to get that message out there to the other people as best I can. Okay, enough of that stuff. Today, we are going to pick up where we left off last class. We're going to finish talking about the moon, the phases of the moon. We'll learn a little bit about eclipses, and then we have to get back to talking about how the sun, the moon, and the stars travel across our local sky. We're going to practice some of those coordinates we learned on Wednesday, and we're going to learn a new coordinate system called the equatorial system. So let's get into that now. I'd like to show you guys a slide of the phases of the moon that we should have constructed in our notebooks last time. And I want to ask you all a few questions to see if you understand what's going on. Okay, so this is very similar, slide 83, to the picture that we all made in our notebooks last time, showing you the various configurations the moon makes with the Earth and the sun to create the phases of the moon. Remember that in this diagram, the sun is over to the, okay, the video is backwards. The sun is over to the right-hand side, okay? Or sorry, yeah, it's my right, and so hopefully it's your right too. The Earth is here, and the moon on any one day is usually stuck in one of these positions. Roughly how long does it take the moon to go around Earth? Do you guys know? How long does it take the moon to orbit Earth? Just take a guess.
30 days, a month?
It's about a month, right? It's going to actually turn out to have different periods depending on whether you're counting the phases or watching its orbit, but it's close to a month. But the Earth spins in 24 hours. So on any one given day, the moon will usually be in one of these positions, and it sits there all day while Earth does a little spinny, winny, winny, okay? Now I'm going to try to ask you guys a question here. Suppose the phase of the moon is new. The moon during the day will rise in the east, cross your meridian at its highest point in the sky, and set in the west. Class, what does the meridian mean? What is the meridian? Who can tell me what the meridian is? Because, see, I need to use some fancy vocab terms, and I ain't so sure that y'all remember what they mean.
The meridian is the area that rises due north and reaches the zenith and sets due south.
Okay, I want to correct your speech. Not area, it's an arc. Not an area, but an arc. But other than that, you did good.
I just couldn't read my own writing. I do have arc.
Oh, you do have arc. Okay, cool. So let's just look here for slide 68. What he said there was, it's an arc that starts due north, comes up through your zenith, and it sets due south. And I'd like to remind you guys that the meridian is like the high point in the sky. If the moon rises in the east, its highest point in the sky will be when it crosses the meridian, and then it will sink back down west, okay? So it's basically a north-south line that cuts the sky in half. Okay, let's get back to that moon diagram for a second. Let's see if we can hunt back to the moon here. Ooh, okay. Class, what time would the new moon cross your meridian? Can anyone answer me that question? What time does the new moon cross your meridian? That's a tough question, right, Eva? Why would
Yes. I wanted to say 3 o'clock, but by looking at the
I want you to look
drawing
at
that we did last time.
Okay, remember, Eva, that each of these little sticks sort of points towards a local observer's meridian. If you're an observer and you're standing here, for instance, your meridian points up, and your horizon is a line that goes through the center of Earth. This is your eastern horizon. This is your western horizon. And as Earth spins, your eastern horizon goes in this direction, and your western horizon goes in that direction, and your head spins around. You know, as Earth spins, your head points in different directions in space, right? Based on that piece of information, can anyone guess what time the new moon will cross your meridian?
Wouldn't be 6 p.m.
No. At 6 p.m., you would be here, and the new moon would be on your western horizon, rising. I'm asking what time the new moon will cross your meridian. Keep trying until you guess correctly.
Midnight.
Nope. At midnight, your head points over here. Your horizon line goes like this, and you can see all of this part of the sky. The new moon isn't even up at midnight. What time does the new moon cross your meridian?
Is it noon?
There you go. Who said that?
Jenna?
Nicely done, Jenna. Okay, the new moon crosses your meridian at noon, because at noon, your head points in the direction of the sun. That's when the sun is at its highest point in the sky. And apparently, that's when your head also points towards the new moon. That's when it's highest in the sky. Okay, Jenna, since you're so good, can you tell me this? What time would the new moon rise?
6 a.m.?
Very good. And what time would the new moon set?
6 p.m.?
Very good. Jenna, you are my favorite student today. Okay, so look, let's see how she did it, okay? Jenna realizes that her meridian, I'm sorry, this is the horizon, and this is her head at 6 a.m. At 6 a.m., her head is pointing down, and this is the eastern horizon because the Earth is spinning like so, and we can see the new moon is coming up over the eastern horizon. As her head spins towards noon, it crosses the meridian, and later on in the evening, when your head points in that direction, then your horizon goes like so, and that's when the new moon is setting below the western horizon. Nicely done. Let's take a note about that, Jenna, because I think that could be like an important thing that I would ask you on a test or something. That's definitely the kind of thing that I could do. All right, so let's talk for a minute about the new moon. The new moon will rise at 6 a.m. It will reach your meridian at 12 p.m. It will set at 6 p.m. In other words, we have just learned that the new moon is up all day. That's one of the reasons why you do not see the new moon. Not only are you looking at the dark side of the moon, the unilluminated side, but it's up during the day when it becomes very difficult to see anything because of the blue sky. Okay, let's see what we've learned. We're going to now try the full moon. We're going to figure out its time of rise, its time of meridian, and its time of set. Jenna, you will not answer because you've already proven yourself in the great halls of famous astronomers to understand what's going on. Someone besides Jenna has to try now. What time will the full moon cross your meridian?
Midnight.
Very good, Ryan. Ryan, can you tell me what time the full moon will rise?
6 p.m.
Very good. And what time will it set?
6 a.m.
Excellent. He can see that when his head is pointing in this direction, his horizon is perpendicular. This is the leading eastern horizon. And as Earth spins in that direction, the moon will come up at 6 p.m. It will cross his head when he points towards the moon at midnight. And then when his head points down here towards 6 a.m., here's your horizon. This is the eastern side where the sun is rising, and this is the western side where the sun is setting. All right? Very good. Let's take that as a note, Ryan and friends. It will rise at 6 p.m. It will cross your meridian at 12 a.m. and it will set at 6 a.m. In other words, the full moon is up all night. I know there's a little bit of glare there. Maybe I should. You know what's tough about one of the things I discovered today about teaching from home during COVID? No more snow days, right? Remember snow days when we used to get the day off? That was kind of fun. Well, I guess that's something that we don't get anymore. Okay. John doesn't get snow days. He has to work on the turboprop planes, whether it's snowing or not. So he's not sympathetic to us. And it's much colder. Okay. Guys, let's try a different question. What would be the best time of night to observe the first quarter moon? Let me ask these questions in a consistently weirder way. You can't hear me? Oh, okay. Sure, Jenna. We'll see you when you come back. What would be the best time of night to observe the first quarter moon? Let's say you wanted to take a photograph with your camera. What would be the best time to take a picture of the first quarter moon?
6 p.m.
Yeah, who said that?
Michael.
Michael, how'd you know that?
I mean, just based on the prior answers from the other students, really, and what you
Right,
said about the
but-
meridian.
But when it's at your meridian, it's the answer I wanted you to say, Michael, is
Yeah,
the best time to photograph it is when it's at your meridian
precisely.
because it's highest in your sky, right?
Exactly.
Good. Okay. So you guys can see that the diagram that we made is actually a very sophisticated tool that can help you figure out whenever the sun or whenever the moon will rise or set on a particular night. And so it's a useful map in that way. Let's try one more question. Suppose it's 3 a.m. and you're drunk and you're stumbling out of the bar. This is pre-COVID times, okay? It's 3 a.m. and you're drunk and you're stumbling out of the bar and you look to the east and you see a crescent moon, at least one of them, rising above the tree line. Is that a waxing crescent or a waning crescent moon? If you're leaving the bar at 3 a.m. and you see a crescent moon rising in the east, is it a waxing crescent or a waning crescent?
Waning.
Waning crescent is correct, because if your head is pointing in this direction, your horizon line is perpendicular, and the only crescent moon that you could be seeing rise in the east is a waning crescent. The waxing crescent moon could not be up at 3 a.m. One way I like to think about it, guys, is the waxing crescent moon is the crescent moon that you see around dinner time. The waning crescent moon is the crescent moon that you see if you've stayed up too late, or let's say gotten up too early, which is even worse in my opinion. Okay, so use this to figure out the times of the rising and settings of the moon, and you too will be able to keep track of the phases of the moon. In fact, you might even get yourself one of these. Hold on, show and tell time. Someone was kind enough to purchase for me a beautifully illustrated Alex Thibodeau lunar calendar for 2021. I'm going to take this out of the wrap for a second so that you guys can see it through the camera. Just a little show and tell time to make class a little more fun today. Look how beautiful this thing is. It shows you the phases of the moon throughout the entire year, every single month. These empty circles are the new moon, okay? And the full moon might be harder to see, but they put these little illuminated dashes around them so you can see what's going on. It's just a really cool, I keep this above my sink and I'm always keeping track of the phase of the moon. Today, I think, is February 1st. Oops, everything's backwards here. So it looks like we're in a waning gibbous phase of the moon right now. Lunar calendars are kind of fun. Later on, I'll talk about why the new moons are always drifting back by 1 day per month. It's because the phases of the moon are actually slightly less than a calendar month. They're 29.5 days. Okay, so that was a little show and tell time for the class there. It looks to me that if this picture were all there was to it, then anytime you had a full moon, the moon would be behind Earth and you'd get a lunar eclipse. And it looks like every time there's a new moon, the moon will be between Earth and the sun. And that seems to suggest you'll get a solar eclipse. Class, why don't I get eclipses every single month? How come every full moon is not a lunar eclipse, and how come every new moon is not a solar eclipse? Does anyone know the reason for that?
Is it because the moon doesn't cross over the sun?
Kind of, a little bit, yeah. The better way to say that, Yudi, is this is a two-dimensional picture, right? So it kind of makes it look like Earth, moon, and sun are in a perfect alignment. But in fact, the orbit of the moon is inclined with respect to the ecliptic plane by 5 degrees. And what that means is, I've got a little moon globe here, but let me do this with these like moon balls because they're a little better, okay? Let's say the blue ball is Earth, and let's say the red ball is the moon. The 2D picture makes it look like every time there's a new moon, it's going to come between you and the Earth. But what's actually happening is the orbit of the moon is inclined with respect to the ecliptic plane. So a lot of times you'll have a new moon that is in between Earth and the sun, but it's a little bit higher above the ecliptic plane. Or sometimes you can have a new moon that's a little bit lower and below the plane of the ecliptic. Here the camera is sort of the sun, right? So these could both be new moons, and these could both be full moons. Your full moons, let's look at a diagram from your book. They actually did a better job with this than I was doing with my moon balls. They have this very lovely picture where they imagine the ecliptic plane as a sort of two-dimensional sheet of water. And here you can see the moon's orbit tilted by 5 degrees, plunging down in and out of the sheet of the ecliptic plane. A very nice illustration. You'll notice that in this configuration, the moon is only crossing the ecliptic at what phases? Can anyone out there tell me what phase of the moon this is here? Who knows their moon phases really well? What phase of the moon is that? Anyone?
First
Third
quarter?
quarter.
Third quarter.
Sorry?
Third quarter.
Not third quarter. Remember, the moon and everything in space spin counterclockwise.
First quarter.
That's first quarter, because if this is new moon, that's the first quarter, that's full, and that's third quarter. Notice that the moon only crosses the ecliptic plane at first quarter and third quarter, but at new moon and full moon, it's above or below the ecliptic plane, thus no eclipse. However, a couple of times a year, as the moon's orbit slides around, as Earth slides around the sun, there happen to be these alignments where the moon will actually cross the ecliptic plane very close to either new moon or full moon. And in this case, some type of an eclipse will happen somewhere in the world. Usually every year we get 2 eclipse seasons. So there are typically 4 eclipses per year, not always, but typically. That doesn't mean you can see 4 eclipses per year because you have to be in the right location on Earth to witness them. More on that in a minute. For now, let's start by taking some notes about the 2 conditions necessary for an eclipse. There are 2 conditions for an eclipse to occur. The first is that the phase of the moon needs to be either new or full. Let me close the blinds a little bit here. A new moon will give you what's called a solar eclipse. A full moon will give you a lunar eclipse. So that's one of your conditions. The phase of the moon has to be either new or full. The second condition is that the moon must be at a what's called a node. And a node happens when the moon crosses the ecliptic plane.
It's okay. I failed.
Sorry.
By a lot.
And it said,
Pardon me? Does someone need to mute themselves? Just giving you guys a second to catch up to me here. Philemon, give me a thumbs up when you're ready to move on. Okay. So it turns out that during an eclipse, there are different sub-eclipses that are possible. And it has to do with the fact that there are different types of shadows that can be made by an extended opaque object. Take a look at this very nice diagram showing you the sun, the earth, and a giant imaginary piece of cardboard behind it. It turns out that there are two types of shadow cast by an opaque object. There is a partial shadow, which is called the penumbra, which is made by the fact that while rays of sunlight from the bottom of the sun are being blocked by Earth, rays of light from the top of the sun can actually penetrate this part and actually partially illuminate it. There is a part of shadow behind the Earth called the umbra, which is complete shadow, and here all rays of sun are blocked. Those are vocab words, so we should probably take a quick note on them. Two types of shadow. One, there is the penumbra, which is a partial shadow. Second is an umbra, which is a total shadow. Sometimes you can even make these two types of shadow on a chalkboard. I wonder if I could do this. I probably should have planned this demo out before I got all crazy here, but let's see what I can do. Create a spot of sunlight there. Let's see if I can. You have to get, oh, geez. What's the reason why this light source has to be very, very far away? I have done this before, but it's not working for me right now. Okay. I probably should have practiced that beforehand. I think if you have to have a really bright light source that's extremely far away in order to reproduce this. You have to kind of mimic the conditions of sunlight. That was a fail. In any case, these two types of shadow ultimately give us the 6 types of eclipses that we can see. Now, there are 3 types of lunar eclipse and 3 types of solar eclipse. And they have to do with whether the moon is in the penumbral shadow, whether the moon is partially in and out of the umbra, or whether the moon is completely in the umbra. So let's take some notes on that. I was tempted to keep fiddling with the lights to create the shadows, but I could easily spend 10 minutes doing that, and the truth is we don't have that time to spare today. So let's just take a list of our 6 types of eclipses. There are 6 types of eclipses, more or less. 3 lunar eclipses and 3 solar eclipses. Let's make a little table here. The first type of lunar eclipse is called a penumbral lunar eclipse. A penumbral lunar eclipse is when the moon travels into the penumbral shadow of Earth. And actually, these types of eclipses happen all the time, and you don't recognize it. And that's because during a penumbral eclipse, the moon actually just goes through a gradual darkening, and then it gets brighter again over the course of about 6 hours. Because most people just kind of look up at the moon quickly when they're running from their car into the supermarket, if you see the moon, you're not necessarily going to know if it's a little brighter or a little dimmer than usual, because you're just going to look up and think, oh, there's the moon, I can see it. In order to notice a penumbral lunar eclipse, you'd have to stare at the moon for hours, watch it slowly get darker and then get brighter again. And people don't tend to stare at the moon for 6 hours at a time unless they're insane, right? So most of the time, penumbral lunar eclipses happen without you even noticing anything about it. However, the next type of eclipse, which is called a partial lunar eclipse, you definitely notice something is happening because you actually see a bite getting taken out of the moon, and it looks kind of cool. And that's called a partial lunar eclipse. The third lunar eclipse is a total lunar eclipse. During a total lunar eclipse, the moon actually moves completely inside the umbral shadow. Now, normally you would think that during a total lunar eclipse, the moon would go completely dark because it's in the total shadow of Earth. But here's something strange happens. Sunlight, when it passes through the atmosphere of Earth, gets refracted or bent around the curvature of Earth. But only the red light from the sun gets refracted and bent strongly enough to strike the moon. The result is during a total lunar eclipse, the moon does get darker, but it turns an evil blood red color that probably scared the willies out of ancient people. And when you see this evil red blood moon happening, you know something crazy is going on. This is a total lunar eclipse. They're really beautiful. We had one a few years back in the middle of January. I think it was maybe 2 years ago. Did anyone see that total lunar eclipse? John did? I remember, John, that it was a brutally cold night in January. And it was like 5 degrees out, so it hurt like hell. And it was around midnight when totality happened. But I
Yeah,
remember...
I was getting pictures of it from my window.
No way. Yeah, I was downtown where there's a
Yeah.
lot of buildings in the way, so I went and stood in the middle of the street and I looked at it, and it looked beautiful and crazy, but I remember it was so painful to stand out there in the ice and snow.
Wasn't that when it was at the biggest point too? We've seen it. It was
Oh,
larger
right.
than
So,
normal.
well, the moon, its orbit is slightly eccentric. So when it's closer to Earth at perigee, the moon is about 5% bigger. So yeah, now that you mention it, it was kind of technically a supermoon. But remember, John, supermoons are only bigger by about 5%, so it's a very slight enlargement. Technically, it's noticeable by the human eye, but it wouldn't have looked super insane. It would have just looked a teensy
Right.
bit bigger.
Yeah.
Okay. I always worry because when I say the word supermoon, I'm worried that people are going to think the moon's going to look like, just massive
Like
thing.
this?
Yeah. It's still pretty much half a degree on your sky. In fact, our homework session on Wednesday will actually calculate the changing angular size, John, and the difference between a supermoon and a regular moon is like 0.48 degrees in angular size versus 0.52 degrees. So it's just a few arc minutes. It's not much. You
Yeah.
know? Okay. But yes, that is a point. It was an eclipse, I think, during a supermoon, maybe, if I remember that correctly.
I think it was.
In any case, if you haven't seen one, you really should. And luckily, there are many opportunities for you to do this. One of the cool things about watching a lunar eclipse is pretty much you have a 50-50 chance of seeing any lunar eclipse, because if you're anywhere on the nighttime side of Earth, you'll probably get to see it. And if you're on the daytime side, you won't. So considering, you know, you get 2 lunar eclipses per year, each year you've got a sort of 50-50 chance to catch one of them. Solar eclipses are more rare only because of the following photograph. Oh, by the way, this is a time-lapse image. People take these beautiful astro art photos, and someone did this beautiful time-lapse image of the total lunar eclipse, going from the full moon to a partial lunar eclipse, totality and back. And it's just, you know, some cool space art shit I want to show you guys.
Well, that's the best picture I have so far.
Oh,
that I could
that's not
find.
bad.
Yeah.
That's not bad at all. And you did that with your iPhone or your phone?
With an Android, yeah.
Oh, wow. Androids have really good cameras. I was noticing, I was hanging out with my buddy and he was taking some photos this weekend. His Android camera was so nice. I think it even has an astrophotography button section on it, doesn't it?
Yeah, if you get the Ultra now, they have that. I only have the regular one. But that was, you were
Makes me
right. That
think
was
about switching
January
brands, to
20th.
be honest.
That was January 20th, 2019.
Oh, wow. Yeah, so 2 years ago.
Yep.
Guys, one of the reasons why it's rare to catch a solar eclipse is because when a solar eclipse happens, the shadow of the moon can splash down somewhere randomly on Earth. And if you're here, you get to see the solar eclipse, but if you're anywhere over here, you don't. And a lot of solar eclipses just kind of pass over the Indian Ocean or the Atlantic without people even getting to see them. There's 3 types of solar eclipses as well. The first is called a partial solar eclipse. That's when the moon is not in perfect alignment with the sun, and it kind of takes a bite out of the moon. Let's take this here. So this is a partial solar eclipse. Then there is a total solar eclipse. That happens when you're in the darkest part of the moon's shadow, in the umbra. And total solar eclipses, as I may have mentioned before, look really wild. The disk of the moon covers the disk of the sun, but you can suddenly see this eerie light from the sun's outer wispy atmosphere called the corona. And the coronal light is very beautiful, but can only be seen during a total solar eclipse. The third type of solar eclipse happens because the path of the moon, as we were just mentioning, is not a perfect circle. So if you end up having a solar eclipse happening when the moon is like a little bit farther away from Earth, its angular size will shrink and it won't cover the full disk of the sun. And we'll be doing this calculation in our homeworks. When that happens, you can get a very magical type of an eclipse called an annular solar eclipse. The angular size of the moon is like 0.48 degrees, a little bit smaller than the sun's, and you get an annulus, or a ring of fire, as the outer disk of the sun pokes out from behind the moon. These are extremely rare and beautiful to observe.
I have a question for you.
Yeah.
The annular eclipse, can you actually look at that or no?
Even a small amount of photospheric light is probably not good for you to look at with the naked eye, because the sun's light is just so powerful. Did I show you the eclipse shades, or was that this class or the other class that I was showing eclipse shades to?
Which one did we have a year or 2 ago? I remember in the summer.
A year or 2 ago, it was a total solar eclipse, but the path.
Gotcha.
So I think I can help here. Let me show you what's going on. NASA's got this lovely eclipse page, NASA solar eclipse. And when you can look up some cool eclipses from some years coming up. And I just want to show you the path of one so you can see what's going on. I think this one, this is a total solar eclipse that's coming up in 2024 of April. I could go hunting from the one that just happened, but I want to show you this one because it's coming up in the near future. And I want to show you the path of the eclipse as seen from the United States. I think I can do that here. So what what happens is if you want to see the total solar eclipse, you've got to be in the path of totality. So the eclipse that we saw last time was like this one in that it passed across the United States. But instead of this one, which is going to go up the United States, that other eclipse came down on a path, a geodesic through the United States. Up in Rhode Island, we were not in the path of totality, so we only saw a partial solar eclipse. But if you go to the location where the eclipse is going to be in totality, then you can see the total solar eclipse. So do you see what I mean? Like when you said what happened a couple of years ago, it was a total solar eclipse. But if you didn't travel to Wyoming or to South Carolina to see totality, you probably saw a partial solar eclipse in Rhode Island. Does that make sense? I was worried that if I told you it was a total solar eclipse, someone would say, no, it wasn't, because I went outside and I saw part of the sun get a bite taken out of it. So in any case, one reason I showed you that total solar eclipse is in 2024, do you guys see the path of totality? It doesn't hit Rhode Island, but it does go through northern Vermont and New Hampshire. And that's only a few hours car ride from here. So I was thinking that could be a worthwhile trip to take in your car is, go up a few hours north and either camp out or just spend the day kind of watching the thing. Okay. These eclipses, we'll study them more as time goes on, but we'll leave it there for now because I have some other things to do with you for today. May I erase, class? Any objectors?
Hey, can I just ask a quick question about some of those terms really quick?
Sure things.
The ones regarding shadows, like umbral and penumbral,
Yep.
are those terms like specific to astronomy or cosmology, or does that apply to just shadows in general?
It just applies to shadows in general. So photographers would have to talk about the same thing. I'm realizing that one of the reasons why I was not able to create the umbral and penumbral shadows is because the sun is a glowing orb, which is actually quite large in its angular extent. My experiment failed after I thought about it some because my crappy little IKEA light that I had handy is a point source. So if your light is all coming from a single point, you're only going to make one type of shadow. But if you have a large object, a large angular object like the sun casting shadows from two slightly different angles, that's when you get the double shadow effect. So any photographer who works with lighting would have to be concerned about umbral and penumbral shadows, as well as astronomers. You might actually think of it more under the subject of optics than astronomy. Okay, today we're going to learn about a new coordinate system, but I first want to start by reviewing geographical coordinates and the horizon system, which I instructed you on last class. And it looks like I'm doing okay on time here. Yeah, I'm doing just fine. So we're going to do a little exercise. We're going to make a drawing of a two-dimensional view of your local sky. And this is a very helpful exercise for you guys. So let's construct a 2D view of the Rhode Island local sky. We will occasionally need to make pictures like this to help us answer tricky questions in our homeworks and in our exams. So we're going to do this just like before. If you have a ruler handy, leave yourself some headroom, and somewhere in the middle of the page, I want you to make a line that's about 10 centimeters long. Then mark the midpoint at 5 centimeters. And then use your ruler to kind of mark where the top of your dome is going to be. So mark a line 5 centimeters above the midpoint. And you might even want to make a few other points about 5 centimeters away to help you construct this dome in an appropriate way. I find that just putting a few dots in here really helps with my dome making skills, which are impoverished in the best of times. Okay, those are just a few dots for me to hit as I construct my dome. And then what we're going to do is just kind of connect the dots, la 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 la, just like Pee Wee Herman. and make ourselves a beautiful two-dimensional view of the local sky. All right. Put an observer at the center of the field. And you can even kind of shade the ground in, even though this is a 2D picture. That's going to be the grass or the ground. We have to put north and south onto here. This is going to be a north to south construction. So remember that I like to put north on the right-hand side, and I like to put south on the left-hand side. It's very important that we specify which direction we're looking. And now what we'll do is we'll construct a line that runs through our observer's zenith. That's the observer's zenith directly overhead. Since this is the Rhode Island local sky, we can also put in the north celestial pole. That should be somewhere pointing up towards the northern part of the sky. Make a line through your observer's foot, somewhere up towards the northern part of the sky. And label that NCP for North Celestial Pole. You guys remember the name of the star that's at the North Celestial Pole, right? What's the name of that star?
Polaris.
Good. Let's put that on our sky. We'll put Polaris right there in the sky to remind ourselves that Polaris is at the North Celestial Pole. Now, drawing the celestial equator is a little more difficult because we're drawing a north to south cross section. And I want you guys to look at a picture of the local sky again here. Let's see. Slide 48. Notice that if we're making a north to south construction, the celestial equator is a little goofy because it's running from east to west. So we can't draw the entire celestial equator, but we can draw this point here. That's the point where the celestial equator crosses the meridian. And so let's make sure that we keep that 90 degrees with respect to the north celestial pole. Okay, so we'll make it 90 degrees. And I'm just going to make a dashed line. And up here, I'll have a little dot, and I'll put CE for celestial equator. Let me increase my illumination a bit. Yeah, see that okay? Get a little closer. All right, I'm going to label, can you guys see that we have 1, 2, 3, 4 angles on our local sky here? I'm going to label those angles with the first 4 letters of the Greek alphabet. Alpha looks like a little Jesus fish. Let me see if this other green marker is a little bit darker here. So here's alpha, okay? Beta looks like a squiggly B. Gamma looks like a squiggly Y. And delta looks like a squiggly D. Alpha, beta, gamma, delta. First 4 letters of the Greek alphabet, and we're using them for these 4 angles. Okay, first question I have for the class goes like this. One of these angles, alpha, beta, gamma, delta, represents your latitude on Earth based on the definition of latitude. And I think someone should actually read that definition out. Whoever has that handy in their notebooks, could you read the definition of latitude for us?
Is it degrees north or south of the equator?
Okay. So based on that definition, degrees north or south of the equator, which of those angles do you think best represents the latitude of that observer there? Can you guys tell me? Which of those would best represent the latitude of the observer?
Zenith.
The zenith is a point on the sky. I'm asking you for an angle. So that answer technically doesn't make sense. Sorry.
Could it be gamma?
Not gamma. I think you guys are going to need some help here. I knew this was going to be a tough question. That's why I asked it. Perhaps I could like draw the Earth underneath here so you guys can see what's going on. Let me use my Frisbee and let's try to draw Earth underneath this person. So here's the Earth, and I'm going to put the observer kind of standing roughly where the observer is in the field. And I'm going to draw Earth's north pole on the diagram here. So that's the north pole of Earth. And I'll draw the equator perpendicular to that. Like so. Then I'll draw a line pointing from the center of Earth to the foot of the observer. Now, think about it, guys. This is the equator. This is the observer's foot. So your degrees north of the equator represents your latitude on Earth. Remember that latitude is an angle. Does that give you a hint as to which angle represents your latitude on the sky?
Beta?
That's right. Because the equator points towards the celestial equator, and your feet and your head point towards the zenith. The angle between the celestial equator and the zenith is the same as the angle between the equator and your feet. And we define that angle as your latitude. So this angle is also your latitude. Very good. That wasn't an easy question. We needed to think our way through that. Okay, one of these angles, alpha, beta, gamma, delta, represents the altitude of Polaris based on the definition of altitude. Here, John, I don't know if that was you that read us the, someone read us the definition of latitude. Could they also read us the definition of altitude?
Degrees above the nearest horizon.
The degrees above the nearest horizon. So which of these angles seems to represent the degrees of Polaris above the nearest horizon?
Gamma.
Either delta.
Whoever said delta was correct. Who said delta?
I said gamma and delta.
Oh,
Phil.
you can't choose two. That's cheating, right?
Yeah, but I know it's somewhere around there.
Well, delta, no, only delta can be the altitude. Why delta? Who can explain that?
Is it because it's the horizon?
Where's the horizon in this picture? Where's the horizon? What is the horizon?
It's horizon is the bar that labeled N, right? It's the line from running south to north.
Ryan, I wanted you to say that because it's wrong. Hold on a second, Ryan.
Yeah,
No, Ryan, you're onto something, but let me explain what I have issue with. This line, Ryan, is the ground. My issue is that the horizon is a ring that goes in and out of the plane of the board. So Ryan, if you had said this point is your northern horizon, I would have been totally okay with that. And this point here, Ryan, is your southern horizon. I'm okay with that. But I'm not okay with saying the line is the horizon. Does that make sense?
Yeah, I understand what you're saying. I just phrased my wording
Sure.
incorrectly.
All I was trying to say, Ryan, is this point is your northern horizon. This is your southern horizon. But remember, your entire horizon is a ring that goes around the bottom of the sky. So this line here cannot also be the horizon. That's all I'm saying. I'm being a little technical with you, okay?
Yep.
Okay, so in other words, what's the nearest horizon to Polaris, Ryan?
It would be the northern horizon.
Good. Now you and I are talking the same talk, okay? That's the closest point on the horizon. And since altitude is degrees above the nearest horizon, delta is the degrees above your northern horizon, okay? Good. Now, remember that we drew this diagram for a Rhode Island local sky. What is the latitude of Rhode Island? I taught you that last time. Come on, guys. Latitude of Providence, Rhode Island.
The latitude is 42 degrees.
North.
Oh, sorry.
You've got to say north so I don't confuse it with 42 degrees south, right? Okay, so let's write that angle into our diagram here. This angle, beta, is 42 degrees. Mark that down. Now, if you look at the diagram, you can see that there is a 90-degree angle, a right angle, between the celestial equator and the north celestial pole. So if beta is 42 degrees, what is gamma? If this is 42 degrees,
Is it 48 degrees?
because 90 minus 42 gives you 48 degrees. Now look, I spy with my little eye another 90-degree triangle, or another 90-degree angle. The angle between the zenith and the horizon also makes a 90-degree angle. So what should the angle of delta be?
42.
42.
Good. And for completeness sake, because I know it's going to be helpful later, what is angle alpha then?
48.
Good. Notice that although we did this for the Rhode Island local sky, it's always true, no matter where you go on Earth, that there's always a 90-degree angle between the equator and the North Pole, and there's always a 90-degree angle between your zenith and your horizon. Therefore, we have just proved a fundamental result that is true for all observers on Earth. And this is a very useful result, and it goes something like this. The altitude of Polaris is equal to your latitude. And that's a fundamental result. Put stars next to it and put it in a box, because that's useful for solving many problems. The altitude of Polaris is equal to your latitude. I know it's snowing tonight, right? But how would we find Polaris in our local sky? What would we do? I guess we'd have to find north. From my location, north is, I'm downtown, and north is like up towards the State House there. And so I would look tonight towards the State House. I'd go up about 42 degrees, which is about halfway through the sky. And that's where I should see Polaris, the tail of the Little Dipper. And you guys can find it in the same way. What if you went to the equator? Where would Polaris be if you were standing on the equator? Say that again, John, you're muted.
I'm wrong. I have to think about that again.
Oh, you're standing on the equator at midnight. Where's Polaris? I'm standing.
90 degrees. That's what I thought.
Okay. The problem is we need to learn how to use the horizon system. Okay. This is a beautiful diagram, but I need to erase it. Has everyone got this down? Does anyone need another minute or two? Okay. I'm erasing. Let's try a couple of sample problems. Here's a sample problem. Describe the location of Polaris in the Rhode Island local sky. How would I answer that question, class?
Would you say 42 degrees north?
That's right. That's exactly right. But let me explain what you just did there and why it's good. We want to use the so-called horizon system. And you, believe it or not, you did do that, although you may not have been conscious of it. Remember that the horizon system has two angles. One of the angles is the altitude, and the other is the azimuth. Whoever said that, I don't know who I heard just now. Oh, Jenna. Jenna, which was the altitude and which was the azimuth?
Altitude was the 42 degrees.
And the azimuth?
48.
No. Azimuth is measured clockwise from north.
90.
Nope. Let's look at the diagram of the local sky together, Jenna. Azimuth is measured along the horizon. You start north, and then you go all the way around. The azimuth is the nearest horizon point to this dot here. What's the nearest horizon to that North Star dot?
Is it the zenith or no?
North
The zenith
celestial
isn't on
pole.
your horizon.
North celestial pole. North.
The North Celestial Pole is on the sky.
Well,
I
north.
don't think you guys even understand what I'm asking you. We have to learn how to talk to each other here. But we're going to work on this, okay? Let me repeat my question. I want you to think about it. Let me clear everything out. Let me start by just redefining things because I think you guys are forgetting shit, all right? This is the North Celestial Pole, the blue dot. The green dot or the green line represents your horizon. It's this ring. The question I asked is, what is the nearest point on the horizon to this blue dot?
Is it north?
That's right. So we
Okay.
need the azimuth of north. Now, what is the azimuth of this point?
I guess I'm just forgetting what azimuth is.
42.
Exactly. You need to know the definitions. Azimuth is degrees along the horizon measured clockwise from north. Your answer should be somewhere between 0 and 360.
318.
No, 318 would be over here.
45.
45 would be over here.
Okay.
It says 0.
That's right. It's 0 because you measure clockwise from north and you are at north. The reason why you answered okay at first is because you couldn't really handle azimuth, so you just said north, and that was fine. So you could say either 0 degrees or north. I suspect you said 42 degrees north because you were just thinking of latitude. You weren't really thinking through carefully. You need to give me an altitude and an azimuth, okay? This is how we use the horizon system. I need you guys to be conscious of it. That's why we tried that problem. By the way, this is going to be a homework problem come Wednesday time. Okay, you ready to try another one? Let's see how you do this time. Question number 2. Describe the path of the celestial equator in the Rhode Island local sky. This is more complicated than the last problem. Let's try to understand why. The celestial equator, unlike the previous problem, is not just a point on the sky. The celestial equator is a whole damned arc through the local sky. How should we deal with this? The best way to deal with this is to describe 3 points along the path. The point where the celestial equator rises, the highest point that the celestial equator will reach, and the point where the celestial equator will set. Those 3 blue dots are the rise, the reach, and the set. And that's what we're trying to do. For each point, we're going to require an altitude and an azimuth. That's a set of 6 numbers. So we'll organize it like this way. There will be a rise point. There will be a reach point. And there will be a set point. For each point, there will be an altitude and an azimuth. Okay, let's start this off nice and slow so that you guys don't freak out. Let's start with the rise point. The rise point, once again, is here. Can someone give me the altitude and the azimuth of the blue dot? Remember that altitude is degrees above the horizon, azimuth is degrees along the horizon.
Would it be 90?
Wait, which one are you giving me?
I don't know, the rise? I don't know, the first blue dot that you have right there.
Oh, no. Okay. Who am I talking to right now?
Yudi.
Yudi, here's the, I need to explain what's going on so that you can understand my beef. You know, like, have you ever been to New York City? Okay. Yudi, suppose you and I were going to go get a drink at a bar in New York City. I was like, hey, I want you to meet me in this pub for a pint in New York City, in Manhattan. And you say, well, where are you, Brendan? And I say, Fifth Avenue. Is that helpful to you? I don't know if you've ever been to Fifth Avenue, but it's like really fucking long, right?
Yeah.
Like I could be anywhere on Fifth Avenue. The only way you know how to find me is if I give you my cross streets. Yudi, I'm at Fifth Avenue and 42nd Street. Now you can find me. The problem that we had is exactly that one just now, except it's for the sky. I want to know the rise point. And so I'm asking you, are you telling me the avenue or the street? And you're saying, I'm giving you the point.
Okay.
Okay, so Yudi.
That's what I meant, the rise.
But hold on, the rise is the point. This point is the rise. But I want to know, are you giving me the altitude or the azimuth? The altitude tells you how many degrees up. The azimuth tells you how many degrees along the horizon.
Okay, I'm giving you the altitude.
Okay, what's the altitude?
90 degrees?
No, 90 degrees altitude would be at your zenith.
Okay.
Is it 48 degrees?
No, 48 degrees would be halfway up the sky. You're on the horizon.
So 90 azimuth and 270. I might be wrong with that.
Oh, God. So you were giving me the azimuth at first, John,
which is
right?
90. Yes.
All right, you are
90.
correct about that part.
I think
Since
I'm
you go
backwards.
clockwise from north, if this is 0, then yes, the azimuth is 90 degrees. But the altitude is the degrees above the horizon. 270 doesn't even make sense.
Yeah,
Because
that's why I was
altitude
wrong with
goes
that.
from 0 up to 90.
Okay, so that would be 0 then, right?
That's right.
Because it's starting from the point.
Because it's on your horizon. Excellent.
Yes.
So let's write that down together because that was a learning exercise. The rise is 0 degrees altitude, and the azimuth is 90 degrees, or you could say east. By the way, 0 degrees east is the same as saying due east because it's on the horizon. Okay, now let's try the reach point. I want to try to get the altitude and the azimuth of the reach point, and the reach point is here. Yeah, go ahead, John.
90 degrees and 180.
Hold on, wait, which is which? You need to specify which.
Altitude is 90, azimuth is 180.
One of those is correct, one of those is incorrect. Your azimuth is right. Jenna, you want to try?
Yeah, is the altitude 48 degrees?
Booyah. Damn, she's good. How did you know that, Jenna? How did you know that the altitude was 48 degrees?
Because
I see that now.
we're measuring it from the ground up into the sky. So that
That's too vague. You know it because you were paying attention during the alpha, beta, gamma, delta game. And you recognize that alpha is the angle between your southern horizon and the celestial equator, and that was 48, right?
Yes.
Okay. You got it from that little picture, right?
Yes, yeah.
Okay, so that's the altitude. What about the azimuth?
And the azimuth is 180 degrees.
That's right. And John had that part correct. You start north and south is 180 degrees along the horizon. Let's write that down. Okay, you guys are getting slowly better here. So the altitude is 48 degrees and it's 180 degrees or south. Okay, now try the set point. Who's getting this here? The set point, of course, is here. Okay, Jenna, because we're crushed for time, why don't you tell us?
Okay, the set point altitude is 0 degrees.
Good, because it's on the horizon.
Yes, and the azimuth is, yep, 180 plus 90.
Which is
270.
270. Very good. 270 is west. Okay, so nice. So the set is 0 degrees. The azimuth is 270 degrees or west, and that's the same as due west. Another way to write this answer would have been to say the celestial equator rises due east, crosses your meridian at 48 degrees in the south, and sets due west. That would have been a classy way to say it that had all of the power and specificity of the horizon system. This is how we use the horizon system. Pay attention to this. Notice that it's not so easy when you have to do it yourself. You have to really understand what those definitions mean, and you have to practice. I can't remember if I told you this last time, but the horizon system is used by astronomers even sometimes when they have fancy telescopes. Like, check out a piece of hardware that really gets my juices flowing at night. And that's a plane wave 1 meter telescope, okay? Oh, what I wouldn't do to have my very own plane wave 1 meter telescope at the Jacobi Observatory. This is much bigger than the telescope we have. It's only $500,000. So perhaps you guys might think about buying me a Christmas present sometimes. And you can see here that this piece of gear uses an alt-az mount. It uses the altitude and the azimuth system. Let's see if we can find a video. I think there's a video on YouTube, plane wave 1 meter telescope in the room slewing around. I just want to show you this. It's in their clean room here. Oh yeah, here we go. So check out how this bad boy works. Telescopes that use an altitude azimuth mount are basically using those two coordinates that you were just practicing with. And here, the engineers in their clean room are testing out the scope and they're slewing it around. Notice that, here, let's hit play on this puppy. You can see that they're slewing it in azimuth when they rotate around on the axis of that thing, but those fork arms hold up the telescope. Here you'd see it zipping around in azimuth, but the fork arms can also move up and down to slew up and down in altitude. And that means you can track stars as they move across the sky, provided you have, here we go, now we're slewing both in altitude and in azimuth. Now that's a beautiful piece of machinery right there. You can take some mind-blowing pictures of galaxies with that thing, and you can do some cool professional grade astro research. So if any of you have a spare cool $500,000 floating around in your back pockets, feel free to think about me come Christmas time, okay? Anyways, the horizon system is nice if you want to go out to the telescope with your Grammy and you want to point the Grammy, you want to tell your Grammy to point the telescope at the Orion Nebula, because you can say, Grammy, could you point the telescope at the Orion Nebula? And you know Grammys, they're going to say, I don't know where the Orion Nebula is. And you say, look, that's easy. It's at an altitude of 30 degrees in a direction west. And then you Grammy slews the telescope west, up 30 degrees, bam, you got the Orion Nebula. The problem with the horizon system is that over the course of the night, the Orion Nebula is going to rise and set and change its position, all right? So let's get rid of this for a second. And let's look at that picture of the rotating sky that I showed you so many times before. Maybe your Grammy will point your telescope at the Orion Nebula, and maybe the Orion Nebula will be 30 degrees above the western sky. But as the night goes on, the Orion Nebula will slowly sink down and it will set below your horizon, and then it's gone. Furthermore, what if your Grammy isn't with you at the telescope? What if she's in Pensacola, Florida, and she's got the plane wave 1 meter down in Pensacola, and you call her up and say, Grammy, I need you to point the Orion Nebula, the telescope at the Orion Nebula. And if she says, well, I don't know where the Orion Nebula is, you'll say, well, that's easy. It's at an altitude of, wait a minute. If the Orion Nebula has an altitude of 30 degrees in Rhode Island, can I trust that it will also be 30 degrees in Pensacola, Florida? Probably not, because you could see that the altitude of Polaris will change, and so will the altitudes of all the other stars. What's really annoying about this is if you and your Grammy discover a new nebula and you want to name it the Grammy Nebula so that everyone knows that you and your Grammy discovered it, well, then you're sort of in trouble, because how do you find a fixed position on the sky if it's always moving around? The answer is that we need another coordinate system, a coordinate system that will stay stuck to the sky, so that if you find a nebula over here in Leo Minor, you can tell everyone, hey, this is the coordinates of Grammy's nebula, and this is her nebula because she discovered it. No one else can claim it now. So what we're going to need is we're going to need a kind of latitude and a longitude for the sky. And that's the professional coordinate system that astronomers use. It's called the Equatorial Coordinate System, and it's the basis of your labs today. All right. Let's learn about the Equatorial Coordinate System. It's latitude and longitude for the sky. Unlike the horizon system, which is a local sky coordinate system, the equatorial system is a global sky coordinate system. It uses two angles that have funny names. One of the names is declination. The other angle is called right ascension. Astronomers have nicknames for these coordinates. Declination is sometimes called dec, and the right ascension is sometimes called RA. Taken together, they're kind of like latitude and longitude. The declination is sort of like lines of latitude for the sky. The right ascension are kind of like lines of longitude for the sky, but they work in funny ways. Okay, so latitude was defined as degrees north or south from the equator. Declination is similar, but it uses positive and negative. The definition is the degrees of a star measured positive or negative from the celestial equator. So for instance, the north celestial pole has a declination of positive 90 degrees. Compare that to the North Pole of Earth, which has a latitude of 90 degrees north. Right ascension is a little weirder. Right ascension is actually measured in hours, not in degrees. Now, do you guys remember what the definition of longitude was on Earth? What's the definition of longitude? Go ahead and regurgitate it from your notes.
Longitude divides Earth into eastern and western hemisphere.
But that's not the definition that I gave you. That is true, but that's not the definition of longitude.
A prime meridian.
East or west.
It's related to the prime meridian.
Oh, sorry. Degrees measured east or west of the prime meridian.
There you go, Jenna. Okay, Jenna, suppose I took this ring and I lined it up with the prime meridian. Notice that as Earth spins in a 24-hour day, the prime meridian will keep pointing towards different places on the sky. So you can't use the prime meridian as your starting point for right ascension. Instead, we're going to use a point that's on the celestial sphere itself. The point that we chose to start our right ascension with is a point known as the Spring Equinox. Let me see if I can show this to you here. The Spring Equinox is a point on your local sky. Rats. Sorry, I thought it was in this slideshow. Nuts. Maybe it's in here. Okay. This is fine. 32. The spring equinox is a point on the globe where the ecliptic intersects the celestial equator. Okay? The ecliptic, you'll remember, is the path that the sun makes around the sky throughout the year. So this point, the spring equinox, is where we're going to start our right ascension from. Instead of measuring it in degrees, we're going to measure it in hours and minutes in a 24-hour clock, and we're going to do it eastward. So for this star here, its right ascension would be, if this is 0 hours, we go all the way around the clock in 24 hours. So you can see, since they've gone about this far around the clock, it's about, around the sky rather, it's 18 hours and 35 minutes. So remember that we define eastward as counterclockwise in space. By the way, you might wonder why it is that I can measure this coordinate in hours rather than degrees. It happens to be a little trick having to do with the rotation of Earth. Earth spins on its axis every 24 hours. And in 24 hours, the sky will rotate 360 degrees. Take your calculators, class. What do you get if you divide 360 degrees by 24 hours? Hey there, little gal.
15.
Eva, what's her name?
It's Lena.
Lena, hello. Welcome to astronomy class. What did you get when you divide those things, guys?
She was actually asking about the class and the different things you had up.
Oh, cool. Anytime, Lena, you're always welcome to hang with us. What'd you guys get when you did the division?
15 degrees. I'm sorry, just 15. Just 15.
It's exactly, watch this, it's 15 degrees per hour. And that's pretty wild that it comes out so even. That's not a coincidence, by the way. That's because of the ancient Babylonians. The ancient Babylonian mathematicians divided the rotation of the sky into 15 wedges, each which were 1 hour. So in astronomy, there's this weird conversion factor, which normally doesn't make any sense, but it makes perfect sense in astronomy. 15 degrees is equivalent to 1 hour of sky rotation. And that's something kind of cool. We can measure the rotation of the sky either in degrees or in hours. Okay, now you're ready to learn the definition of right ascension. The definition of right ascension goes like this. It's the hours and minutes measured eastward from the spring equinox. Usually we display it in a kind of 24-hour military clock. Okay, guys, just as we kind of needed practice with the horizon system to sort of get it and to have things click in our minds, we're also going to need to practice these two coordinates, right ascension and declination, for it to kind of click in your minds. Part of what we're going to do in our lab today is we're going to actually find stars using these coordinate systems. But I thought we could play a little game where we could test you guys and see if you can figure out the answers to some things. Some people are still writing. So Jenna, let me know when you're all done copying stuff down. You're good? Is anyone else still writing, or can I erase? Okay, woo woo. Here we go. I'm erasing. Okay, here's a little sample problem. This will be the last thing we do before we take a little tea break today, okay? I want you guys to help me find the right ascension and declination of the 4 key points on the celestial sphere. You'll remember the 4 key points are the spring equinox. We're going to have a right ascension and a declination. We have the summer solstice. We have a right ascension and a declination. We have the fall equinox, right ascension, declination. I'll show you guys a picture in just a second that will help. I'm just kind of setting it up for you, okay? And then we have the winter solstice. Right ascension and declination. Let me show you what this looks like on the globe. Bada boom, bada boom. We could use this picture, but let's jazz it up a bit. Let's try this picture, which is tilted a little bit sideways. Okay, first order of business. Let's see if you guys just throw yourself into the pool and see if you can swim here. Here's your point. I'll mark it with yellow for the sun. What is the right ascension and the declination of that point, the spring equinox? Can you give me either one of those coordinates? Geez, not everyone at once now. Take your turn.
Would the right ascension of the spring equinox be 0 hours?
Excellent. Who said that?
Ryan.
Ryan, I like you. You're very good. Because it's on the spring equinox, you're 0 hours away from the spring equinox. Ryan, we have to write it like a military clock, sort of like a 0000, okay? Ryan, are you brave enough to also try the declination, the degrees above positive or negative from the celestial equator?
Would it also be 0 degrees?
That's right, because you're on the celestial equator. Nicely done, Ryan. Ryan's with me. Let's see if someone else can get one. Let's try a harder one. Can you guys, and Ryan, let's let them try first because you're already understanding, so it's less useful for you, but I'll let you try if they can't get it. Can anyone give me the right ascension and declination of the summer solstice? Or give me one of them. So we talking about this point right here. Oops. What do you think? I need a right ascension or a declination. Jenna, want to give it a whack?
Is 90 degree?
Which one are you giving me, first of all?
That's what I'm not sure about.
All right, we got to be sure about that. Do you want to give me right ascension or declination? Why don't you start with declination? Declination, I think, is easier. What's the definition, Jenna, of declination?
Degrees positive or negative from celestial equator.
So the red ring is the celestial equator. How many degrees above the celestial equator do you think that is?
23.5.
Excellent. It tells you right there. The only critique is positive 23.5, okay? How about the right ascension? Jenna, what's the definition of right ascension?
Right ascension is the hours and minutes measured eastward from the spring equinox.
Okay. So I'll remind you that it's a 24-hour rotation around the sky, and it looks like you're about a quarter of the way around the sky.
So 8.
Try again.
Oh, 6.
6 hours.
Hours.
You're a quarter turn around the sky. Good. Okay, Jenna has passed her test. Can anyone else pass the test besides Jenna and Ryan? What about the fall equinox? Is anyone starting to figure this out now?
The RA is 0. No, I'm sorry, 12.
Very good, because you're a quarter turn around the sky. Yes, the RA is 12 hours. How about the declination, Eva?
That I believe that's 0.
That's right, because you're back on the celestial equator. Nicely done. Way to go, Eva. Okay, so the fall equinox has a right ascension of 12 hours and a declination of 0 degrees. Okay, someone besides Eva and Ryan and Jenna, can you get the winter solstice for me? What would this guy be?
No time to explain. Grab a cactus.
1800 and 23.5 degrees negative.
Excellent. Negative 23.5 deck, 1800 hours right ascension. Good. Okay, so that's a first little practice problem. Of course, our labs today will help you develop that a little bit more. Nicely done, guys. Keep those handy. Those give you some examples of how to find right ascension and declination. And examples really help you understand what's going on. Well, it looks like we've used up most of our lecture time for today. Oh gosh, it's 1:36. Actually, by my computer clock, it's probably good. Where's my computer clock? Go to gallery view. 1:32. Okay, not so bad. Now it's going to be time for our lab. We're going to do lab number 2. Guys, as usual, we'll take a little, 15-minute break or so. Does everyone like that little break in between lecture and lab? No, I know you might have just got here, but we need a little psychic break before we go on to lab, okay? So right now on my iPhone, it says 1:37. So maybe at like 1:50, 1:55, I'll take a little 15-minute break. Then we'll come back and we'll get to our lab number 2. Sound like a plan? I'll be pausing the video until then. Don't let me forget to unpause the video. I did that last time and it was terrible. The other issue is, oh, I've got a note to self, hit record. If you just joined us like Noah did, make sure you print out the first 2 pages of lab 2 that I gave you. You're only going to need the first 2 pages, okay? Okay, guys, so I'm going to take a little tomato sandwich break and I'll catch you in 15 minutes. Over and out. Okay, everyone, welcome back. It's time for our second lab on the celestial sphere. We're going to practice using some of those coordinates that we just learned about in our class. Let's go ahead and just talk about a couple of sort of pre-game things before we get going here. I want to talk to you guys about constellations for a second. Constellations are more than just those stick figures that we draw on the sky. Constellations are actually areas or territories on the sky. Does anyone remember how many constellations there are in the entire celestial sphere?
$13.
There are 13 zodiac constellations. There's more than just the zodiac, right? I thought maybe someone would remember how many constellations there were.
Is it 88?
Nice. Riley got it, and so did someone else. That's excellent, guys. I'm proud of you. So 88 constellations are recognized by the International Astronomical Union. And what the group of astronomers have done is they've kind of blocked off these territories on the sky that sort of follow the boundaries of the constellations. And anywhere you go on the celestial sphere, you're always in one of the 88 constellations. That's important because today on our celestial sphere, the boundaries of our constellations will be these sort of dotted blue lines. And when we find a galaxy or a star, we'll have to make sure that we can identify which constellation it's in by kind of checking out the boundaries for those territories. I think that's the only thing I needed to tell you beforehand, that constellations represent areas in the sky. Let's see if we can go to iPhone mode here. I've got this borrowed iPhone 7 from last time. We'll see if it works this time. Share screen, iPhone. Okay. Excellent. All right, it's going to be a good computer day here. Come on, baby. There we go. Okay. Let's take a look here at our lab. For starters, we will put our names down. Up here, we will put lab number 2 so that we keep track of our submissions. And for our lab section, AS1010, and by now you guys should know what section you're in. You're either in 001 or 002, or sorry, the night class is 104, okay? So you're in one of those sections. In table 1, they've given us the coordinates, the right ascension and declination of the 10 brightest stars in the sky. Our job is to find their names and to find the constellation that they're in. Let's take a look at my globe here and see what's going on. So there's going to be a little bit of glare. That's going to make this difficult. I can use my cue cards here to kind of help with that, I think. First of all, the names of the stars are written in black. The names of the constellations are written in blue. The reason why they're backwards is because you're supposed to look through the globe and then read from the other side. But I'm going to have focusing issues with that. It'll be easy to focus on the backwards stuff in front of me here. So let's just orient ourselves on this globe for a second. The seam of the globe is the celestial equator. That, of course, has a declination of 0 degrees. And then we go positive when we go up. This is positive 10 degrees declination. Let's see if I can get my cue card in there. Positive 10 degrees declination, positive 20 degrees, positive 30, positive 40, positive 50, all the way up to the North Celestial Pole, which is at positive 90. If we go down, it's negative 10, negative 20, but they didn't really put the negatives on there. The hours of right ascension can be seen here. That's 0 hours. There's 1 hour of right ascension. There's 3 hours of right ascension. And we can even use this tick mark up here to estimate the minutes. The big tick marks are 20 minutes and the little tiny tick marks are 4 minutes. It looks like our very first star has a right ascension of 6 hours, 43 minutes and negative 17 degrees. Let's see if we can find, oh, by the way, one last thing. The stick figures of the constellations are solid blue lines, but these dotted blue lines mark out the boundaries of the constellations. So we'll have to make sure that we kind of identify constellations without crossing the dotted blue lines there. Let's try to head over to 6 hours and 43 minutes. So here, you guys can see 6 hours and 7 hours of right ascension. And you know what I'm going to do? I'm going to get some tape here. I'm going to see if I can't make something that will stick to the globe. So I'll put some tape on this cue card there. Put a little piece of tape on that there. And that ought to let me kind of stick my cue card to the globe a bit so I can have my hands free. Okay. So, I don't want that. I just photo. Okay. Sorry. Here, guys, you can see the 6th hour of right ascension. There you can see the 7th hour of right ascension. 6 hours and 43 minutes should be about 3/4 of the way between the two. That, after all, is 6 hours and 40 minutes, and that's 6 hours and 43. So we're going to start there, and then our declination is minus 17 degrees. Down 10, down 20, and that looks like minus 17 degrees. What's our star, class?
Sirius.
Sirius, the Dog Star. And what's the constellation there? Can you read that?
Canis Major?
Major, Canis Major, the big dog.
Oh.
So this will be a little difficult since it's backwards, but we can handle it. So Sirius, Sirius is the brightest star in the sky. And it's known as the Dog Star. It's actually up at this time of year. And that's Canis Major, the big dog. All right, next one is 737 and positive 5. 737 and positive 5. Okay. So you guys got the swing of this now? There's 7 hours. Eight hours. 7:30. Let's see. That's 7:20, 24, 28, 32, 36. So about there. Start at the celestial equator and go up positive 5. What's our star?
Procyon.
Procyon. And the constellation?
Canis Minor.
Canis Minor, the little dog. Procyon is our star. and Canis Minor. In Latin, C's were always hard C's, never soft C's, so they were Procyon. Okay, 2040 and positive 45. We're gonna have to wrap around the globe for this one. See if I can grab that. 2040. Just a moment, class. So there's 20. So there's 20. That's 2040. And let's go up positive 45, positive 10, positive 20, positive 30, 45. What's our star?
Deneb.
Deneb and the constellation?
Cygnus.
Cygnus the Swan. Nicely done. Deneb, I think, is the tail of the swan. These are all legendary stars. All right, 1948, positive 9. 1948 should be almost at 20. Positive 9 brings us up to this star here. Ow, my back hurts. What's our star? Altair. Talk to me, peoples.
Is it Altair?
Altair. What's the constellation? Can you tell?
Delphinus?
No, Delphinus, you'd have to cross the dotted blue line.
Oh, yeah.
It's actually, I sneaked you.
Judah?
It's over here. It's, hold on. You guys can't see it without my cue card being moved. It's called Aquila, the eagle.
Oh.
A-Q-U-I-L-A. So I tricked you, sorry. Altair. And that's in Aquila, the eagle. Sorry, guys, I'm still choking on pepper from my tomato sandwich. Oh, okay, I really went a little overboard. Let's see what we got next. We got 513 and positive 46. Let's go back over here. I need more arms. 513, positive 46. So here's 5 hours, and that's 4, 8, 12, 16. So we should be about there maybe. And now we got to go up positive 46 from the celestial equator. So 10, 20, 30, 46. Who's our boy?
Capella?
Capella. And the constellation, let's see, Capella's connected to this constellation, which is here. It's Auriga, the herdsman. Okay. Okay. Next up, we have 513 and minus 8. So there's 5. 513 is like a quarter of the way. So that's 5 hours. That's 6 hours. So a quarter of the way is 513. And then minus 8 is almost down at minus 10. What's our star?
Regal?
Rigel. And you can see that Rigel is the lower foot of Orion. 14 hours is on the other side of the globe. I'm temporarily going to jump ahead, and I'm going to jump to this one. I want to do 5:53 and +7. Let's see here. There's 5 hours. 5:53 is almost at 6 hours. And +7 brings us to what famous star? Do you know what this is? Someone's chatting me here. Betelgeuse, says Ryan, correctly. And that's also in Orion. Betelgeuse is the famous red star in the shoulder of Orion.
Wasn't there speculation like last year or something that it was getting dimmer?
It wasn't speculation. You could see it with your own damn eye.
Oh no.
So the speculation was what was causing it. If you remember, I showed you guys a picture at the beginning of class where I showed you what Orion looks like in the nighttime sky. I've looked at this constellation for years, and Betelgeuse, which you can see here, has always been much brighter and redder than the stars in the belt. I kid you not. I was out there last year looking at that Betelgeuse, and it was clearly dimmer than the 3 stars in the belt. I had never seen anything like that in my life. Now, there were 2 theories as to the speculation was what was making it go dim. Sometimes stars, before they go supernova, undergo a catastrophic collapse where the star material all collapses inward and then undergoes a kind of tremendous explosion and pushes the star out. So some people thought that we were witnessing the beginning of the supernova because they thought the star was shrinking and getting dimmer. It turned out that the main explanation of what happened was that Betelgeuse is so big and tenuous that it sometimes spits plasma off of its surface, and the plasma then collapses and condenses into a dark cloud. And that dark cloud was blocking some of the surface of the star and making it dimmer. But that, if that was you, John, who asked about that, that was a huge deal in astronomy.
It was Michael.
Oh, sorry, Michael.
I heard it was a Dyson sphere.
No, well,
no, I'm just kidding. I'm just kidding.
That's a possibility, I suppose, right? It could be that aliens have surrounded their star with a giant solar panel bag. But that being the case, since last year, Betelgeuse has since gotten brighter again and seems to have stabilized a bit. But I have to tell you, it's still a bit dimmer than this. If you took a photo today of Orion, Betelgeuse would not look as bright as it does in this photograph. I only know this because I was out there, Michael, a couple of nights ago. I was taking a walk through the jewelry district, and I looked up at Orion, and I was like, you know, Betelgeuse never got its luster back. It's just a
It's
little
so neat.
Yeah, it's so wild, right? Stars are usually kind of consistent. They don't usually fuck around in short human timescales. So to see a star change its brightness like that was just totally unheard of. It was so cool. I'm glad you brought that up. Okay, let's go hunt for the star that's located at 14 hours and 10 minutes and +19. So we'll go over to, just give me a second to fiddle here. 14 hours is like, woo. Okay, I don't think I can get my cue card over there because it's too far away. So we're gonna have to fight a little bit of glare if you guys can handle it. Okay. 1410 +19. So here's 14, and 1410 should be about there. And I can already see the star. +10, that's almost +20. What's my guy? Let me get my slideshow back here. I want to be able to see what you guys are seeing.
Arcturus?
Arcturus, very good. That's Arcturus. They say that you arc to Arcturus. From the handle of the Big Dipper, you arc to Arcturus. And what constellation are we in here? This one's kind of funny. Let's see if you guys can make heads or tail this. It kind of looks like a giant necktie in space, but it's a herdsman. What's the name of that constellation?
Boot?
It looks like booties, but it's actually Bootes. I believe the second O should have an umlaut on it. So you get to try out some umlaut action today. Bootes, with the second O having an umlaut. Bootes. Auriga is a herdsman. Bootes is a herdsman. Orion is a hunter. These are dogs, and that's a swan, and that's an eagle. It kind of makes you realize that ancient peoples who were watching the sky, they had some shit on their brain, and it was sort of like hunt, kill, eat. Okay, which is pretty much, you know, intrinsic human experiences, I guess. Except now we don't hunt quite as much. Let's go to 1627 and -26. Okay, so there's 16 hours. That's 1620, so 1627 would be over here. And then we're going down to -10, -20, and that's -26. What's my star?
Antares? Antares?
Antares, yeah. And you know what Antares means? It means anti-Mars. So people named this anti-Mars because it's a very red star like Betelgeuse. And it was supposed to be the opposite of Mars, Antares. And Antares, where are you there, Antares? Here you are. Antares is kind of tricky to see the constellation. You have to follow this line down. And it's actually part of Scorpius. So this is probably the stinger. This is the scorpion, and that's its little stinger there. Okay. 1836, +39. We'll go to 18. 1836 is about halfway. And then we'll go up +10, +20, 30, almost to +40. What's my star?
Vega.
Vega.
Vega, and the constellation is called Lyra the Harp. These are the 10 brightest and most famous stars in the northern part of the sky. I'd like to encourage you after this class ends, or even during the class, to grab a little constellation chart and see if, or get one of those apps on your phone. And when you're out at night and you're walking around looking at stars, see if you can start identifying some of those bright stars and constellations. It makes the nighttime sky a friendly place, and it's kind of fun. Okay, to do this next part, we're going to have to look up the coordinates of the 5 naked eye planets tonight. They don't print the planets onto the globe. Do you guys know why? Why wouldn't they print the planets on the globe, but they would print the stars?
It could get really confusing.
As you can tell, they have no trouble being confusing. They don't mind being confusing one bit.
The planets aren't stationary.
That's the answer, John. Night after night, the planets are wandering against the background stars. So it's not so easy to print them on there. So what we're going to do is we're going to look up their right ascensions and declinations in a table called an ephemeris. Make a little sort of chart there for RA and Dec. I kind of did mine freehand. And then we'll put the constellations there. I have to look them up. I'm going to use an ephemeris table. Sun to Sedna is ephemeris.com. And I'll grab the coordinates and you guys can kind of write them down for me. These should be for today. Mercury, Venus, Mars, Jupiter, Saturn. Okay. So you can see I've got the right ascensions and declinations there. I'm not going to get into the arc minutes and arc seconds, but I will do hours and minutes and degrees. So for Mercury, it's 2150 is the RA, 21 hours and 50 minutes. And here, I'm gonna just sort of, sorry guys, I'm working on my feng shui. Just bear with me here. Okay. The declination is minus 10 degrees and 38 map. We'll just say minus 11 degrees. Venus is 2010. And the declination is negative 21 degrees. Mars is 2 hours and 40 minutes. And positive 17 degrees. Jupiter is 2051. And negative 18 degrees. Saturn is 20 hours and 31 minutes and negative 19 degrees. I want you guys to notice, can you see that Jupiter and Saturn are actually pretty close to one another in their coordinates? All this year, they've been in conjunction. They've been kind of in the same location. So actually, look, it kind of looks like Mercury's not too far away. But anyways, why don't we hunt around for them? Let's start with Mercury. 2150 and negative 11. So here's 20. Oh, sorry, we want 21. There's 21 hours and 50 minutes. It's almost to 22. And then minus 11 brings us just over this edge here. Now, I don't know if you guys, hold on, let me get the card out. Where's the bloody card? What did I do with that? Oh, it's on the ground. All right. Okay. So, oops. All right. Let me try that again. So 2150 is about there. But negative 11 actually puts us right over that dotted blue line. So it actually looks like we're inside this constellation. You see what it is?
Copernicus?
Nope. Capricornus, like Capricorn. I guess it looks like Copernicus. Venus is 2010 minus 21. So here's 2010 and minus 10 minus 21. It's also in Capricornus. Okay. Mars is 2 hours, 40 minutes, positive 17. So we'll go over here. 2 hours and 40 minutes. Oh shit, I gotta twist this globe up. Okay. 2 hours, 40 minutes, and then 40 minutes is right about there. It's right on that dotted line. And then what is it, minus 17? Oh no. I think we got a problem. I think it's in the hole. 2 hours and 40 minutes is there. Minus 10, minus 20. 17. What is this?
I think it's plus 17, not minus 17.
Oh, is it? You're
Yes.
right.
Yeah, I'm pretty sure it's positive 17.
That's great because there's a big hole down there and I was starting to stress. Okay. Okay. Thanks, guys, for correcting the professor. Good thing out. That was just a test to make sure you were paying attention. And you all passed the test, okay? So let's try that again. So 2 hours and 40 minutes. Now we're going to go plus 10, plus 17. What's our constellation?
Aries.
Aries. Very good. (2051 minus 18). So here's 2051 minus 10. Oh, look where we're back in again. We're back in Capricornus. I think there's going to be 3 Capricornus. That's wild. And this one, I'm guessing, is also going to be Capricornus. 2031. 2031 is about here. And negative 19. Minus 10, minus 20. Yeah. Wow. We've got 4 of our planets in the same constellation. Okay, here's where I'm going to tell you guys a little bit of truth tales, okay? These constellations were based off this globe. But I suspect this globe was constructed either in the 1970s or the 1980s. And I know this because these globes were around when I was a student in college. And they don't make them like this anymore. In fact, can you guys see the construction on these here? Look at this. 1967. Now, that means this globe is kind of old, right? Because if it's now 2021 minus 1967, that globe was made over 50 years ago. Every 50 years, you have to correct the positions of the stars because the moon's effect on the Earth is to cause something called precession. And precession causes the Earth to wobble, and it shifts the orientation of the Earth relative to the planets and the constellations. So if I look at the cheat sheet of the correct answers today, you'll notice that in the last 50 years, the planets have all drifted by about a month or so. So instead of getting Capricornus, Capricornus, Aries, Capricornus, Capricornus, they've got Aquarius, Aquarius, Taurus, Aquarius, Aquarius. So the actual constellations that the planets are in tonight have drifted a little bit because of this 26,000 year precession. It's a very slow effect where Earth is wobbling on its axis. In fact, what it's really doing, guys, let me show you this here. I should have a toy to demonstrate this. Well, it's kind of wobbling like a top. This is actually a tippy top, so it's not the best example. At some point, I'll show you guys a good example of precession. Okay, you know what? Note to self: I need to clean my stupid cart. Okay, I have a top somewhere, but if you ever seen a top do a precessional wobble, that's what Earth is doing. Okay, one more exercise, and then we're going to do something fun, and then we'll stop. In our next exercise, we're going to move the sun to some key dates on the celestial globe, and then we are going to estimate what is the right ascension and declination of the sun on that day. And I want you guys to notice that the sun is represented by this little yellow nubbin, and I can move it along the dates of the ecliptic. You can see here that I've got dates printed along this diagonal line called the ecliptic. It's the sun's path. And that the ecliptic is inclined by 23.5 degrees with respect to the celestial equator. So let's head on over to our first date, which is March 21st. And I'll try to put the tape onto the sun so we can see that there. And carefully move the sun. So here's March 5, 10, 15, 20, and there's March 21st right there. What would you guys say is the right ascension and declination of the sun on March 21st?
Zero hours and 0 degrees.
Excellent. It's on the celestial equator, so it's 0 degrees, and it's on the so-called spring equinox, 0 hours and 0 minutes. Good. Now let's move it over to June 21st. Is this looking familiar at all?
Yes.
What's this reminding you of?
Seasons.
Yeah, the seasons. Spring Equinox.
Okay.
The lecture we just had today.
Yeah, exactly. I was going to see if you guys noticed that. It was sort of a, there's a reason why I did that during lecture today to speed this up. So there's June 21st, right about there. What would you say is its right ascension and declination?
6 hours and 23.5 degrees.
Positive 23.5. That's right.
Positive.
So we have 6 hours and positive 23.5 degrees. Let's just check out September 21st next, okay? So we'll go over here to September. There's September 15, September 20th. What do you have for September 21st?
12 hours and 0 degrees.
Good. 12 hours, 0 degrees. And let's try, just we'll verify that on December 21st, we already kind of guessed what it should be. And there's December 21st, right about there. So what do you have? Shout at me, people.
18 hours, negative 23.5 degrees.
Good. 10. Yeah, it should actually be down there. Okay. And let's see if we can do the sun, and then we'll compare the sun to the actual value today. Is today February 1st, everyone?
Yes.
Yep.
Okay. So once again, we may have an issue with these being coordinates that are 50 years out of date, but let's try it. February. There's February 1st. So there's January 30th. There's February 5th. So I'm guessing that's February 1st right there. What would you say is your right ascension? Read it off the globe.
Would it be 15?
Nope. Look.
21.
21 hours. And what would you say is the declination right now? That's 0. That's minus 10.
12 degrees, negative 12.
12 would be over here, just past negative 10. This is greater than halfway to, that's negative, look, that's negative, oh, I see. You're going off the sun. The problem is the little kid in, you know, whatever, in Bangladesh or whatever, had to construct this, probably didn't have, you have to angle it just right. You know, it's not perfect. We should go off the dates in the ecliptic here. I see why you say negative 12 now, but I would say more like negative 18 or something, or negative 17. Do you see what I'm saying? There's a mismatch between where the sun is and where the ecliptic is. I'm going off the ecliptic. So I would say 21 hours and maybe minus 17 degrees. Shall we compare it to the actual one for the sun today? Let's look at that. They have it on the sun to Sedna. We didn't do too bad. Look, 21 hours and 2 minutes and - 16 degrees and 52 arc minutes. We basically got that spot on. That's pretty good. So 21 hours and minus 17 degrees is pretty damn good. Okay. I got one more fun exercise to do with you. Okay. Now, for our last bit, I want to talk to you a little bit more about that 26,000 year precession. Oh, I just remembered where my top is. Here's my top. So if you've never heard of precession before, it's a physics thing. And I want you to watch what happens. I'm going to give this top a little spin. Whoop. Let's try to keep it on the table. And do you guys see how, let me get this going here. Can you guys see how the top is, all right, it's wobbling in a kind of complex way. There we go.
We're not shared with your iPhone right now.
Oh, you aren't?
Yeah.
That's right. I stopped it. Sorry.
No, you're good. You're good.
I want to show you this because this is cool. Let's hope it works again, because remember last time? Okay, there we go. Oh, fuck, it just disappeared. I hate you, iPhone. This thing is really weird. If you stop sharing it and then you try to share again, it glitches. Hold on, maybe I can do this. Maybe I can do it on this guy. Let's see here. Let me try to share to my personal. This iPhone has a worse camera, but maybe it'll be kind. Oh wait, this isn't connected to the internet. All right. Sorry, I got a point here. I'm trying to make it. Why it gotta be like this? Oh, that's such an annoying feature. Okay, last time you guys showed me how to shut this down. I shut this down like so. Slide power off. Stop the share. Okay, so let me explain what we're gonna do while I'm powering this little ding dong back up here. Power iPhone. All right. You guys know that when you do your astrology. Oh, by the way, someone turned in a homework on this past week, and they wrote at the top of the page astrology 1010. And I literally took a point off their homework for that. Okay, so don't you dare write astrology at the top of your homework. I will literally subtract a point for that, just out of spite, okay? So people who like this, who believe in astrology, they often read their horoscope in a newspaper, or you know how these kids do it these days. They look on their CoStar or some astrology app on their phone. And people have a horoscope that they're supposed to believe in from this. The problem is that the Earth goes through a 26,000 year wobble due to gravitational tugs from the moon. And I was trying to demonstrate this phenomenon. It's called precession. And I was guessing that most of you have not heard of precession before. So let me just kind of demonstrate that to you real quick. My phone's now connected, okay. On this top here, if I give it a little spin, you guys can see that it's kind of doing this wobble on its axis. Can you guys see that little wobble there? All right, well, it's even better if you do it over here. Let's try this. Yeah. That little wobble is called precession. And Earth does this over 26,000 years because of its influence with the moon, and it changes the position of the ecliptic relative to the background constellations. So let me demonstrate what I'm trying to say here. Let's pick a student in this class. Let's pick Jenna. Jenna I want you to give me your birthday, but just the month and the date, not the year.
Okay. It's January 23rd.
Okay. And I want to know, what is your sign supposed to be if you like, you know, look in a magazine like Cosmo, or if you look on CoStar, what's your sign supposed to be?
Aquarius.
Okay. So she's supposed to be an Aquarius according to CoStar or whatever astrology app she uses. The problem is these astrology apps are basing your sun sign on the coordinates of the sun from 500 AD, when the Greek astronomer Ptolemy wrote the book Tetrabiblos. And in the intervening 1500 years, the position of the sun has shifted with respect to the background stars due to this wobble. So why don't we go ahead and let's put the sun on January 23rd, and let's see where the sun was on Jenna's birthday. So here we are in January, we're pretty close. And there's January 23rd right there. Jenna, when you were born, what constellation was the sun in?
Capricornus.
Yeah. So think about this, Jenna. Your real sign, because let's face it, your astrology is supposed to be on where the sun was on your birthday. When you were born, the sun was actually in Capricornus, not in Aquarius. So, Jenna, does that make you a Capricornus now?
I don't know, I guess, technically.
Yeah.
But I don't, yeah.
Oh, yeah, right. So if you don't worship, then that's fine. Okay. If you don't drink the juice, then neither do I. But I'm trying to make a point. And we could try it with someone else. Okay. So like Ryan. Ryan, what's your birthday?
That would be July 1st.
And do you know what your sign is supposed to be according to this?
No idea.
Oh, okay. Well, then you're
To be
cool.
honest with you.
Let's try someone else. What about Eva? Eva, do you know what your sign is supposed to be?
Yes, I was born January the 8th, and I'm supposed to be a Capricorn.
Okay. So you're born January the 8th, and you're supposed to be a Capricorn. But if we go over here to January the 8th, we have crossed the boundary. We're no longer in Capricorn. We're actually in Sagittarius. So Eva, the sun was in Sagittarius on your birthday. Do you guys understand the point that I'm trying to make here? The point I'm trying to make is, if your personality is supposed to be based on where the sun is on your birthday, then why the fuck isn't the sun where they said it was on your birthday? Sorry, excuse my language. I know there's little ones around. In other words, it doesn't make any sense. So keep in mind that if you are going to practice astrology, you might want to update your coordinates for 26,000 year precession and make sure that you get the proper sun sign before you start playing those reindeer games. Okay, so that's all we're doing for today. The result is that we have 2 pages to turn in. We have this page where we did the stars and the locations of the planets. And then we have this one where we did the coordinates of the sun. I'd say we've done enough work for today. Don't you guys think so? All right. So we're going to turn in these labs right away so that we don't forget. And you guys can do that for me, right? Take a picture, upload them. Try to upload them from your computer rather than your phone. That way it doesn't give me the hyperlink, but it actually shows me a preview. On Wednesday, we're going to have a really intense lecture on timekeeping. Anyone who's taken my 1020 class, this is all going to be new stuff that we do for you guys on Wednesday. And then we'll have a very intense homework. On Wednesday's homework is going to be a little wild, so hang on to your hats. Once again, we'll do the homework together. We'll turn it in. No stress, okay? Okay, do you guys need anything else from me today? All right. I look forward to seeing you on Wednesday. Enjoy that snowstorm. Stay warm, okay? Bye.
Adios.
Adios.